So the last thing we talked about were a bunch of theorems and ideas and properties and warnings for these matrices that we're studying. We looked at matrix multiplication, and we said that they were associative, distributive, both from the left and right side. And you have to do the left and right side distributive laws because of the idea that it's not commutative. It's a scalar multiplication associative, and they have an additive identity element, and that's the identity matrix. And if it's not a square matrix, then the identity matrix from the left side is different from the identity matrix on the right side, which is this last thing over here. A handful of warnings from last time. It's not commutative. It doesn't follow the canceling property. You know how we can cancel the A and B equals A and C. We cancel the A's out. The whole idea of canceling doesn't work out so well with this. It actually, you can do that if A was invertible, and that's the inverse matrix is the stuff that we're going to talk about today. And then the zero property doesn't work either. You know how you have the factoring quadratics and you're solving to find the roots. You factor them and you say, okay, then one of them is equal to 0, the other one's equal to 0, or both, then that's how things work out. But for matrices, it doesn't work out like that, again, because of the idea that it has to be invertible. If it's not invertible, then things like this don't happen nicely. Powers. So that's where we're going to pick up from. Powers of matrices. And for us to be able to talk about powers of matrices, powers are, you know, like the powers that we have in whenever we first learn powers. We have to multiply the number by itself so many times, and the same thing with matrices. We have to multiply the matrix by itself a number of times. And in doing so, we need to make sure that the matrices are of the same size. And so we keep it the same size. We ensure that they're going to be the same size if it's a square matrix. So we have to make sure that we're dealing with a square matrix, and then the powers are going to be denoted by the same way we denote powers. It's just repeated multiplication. So technically, I guess I didn't finish here. I meant to write when you have a power applied to a matrix applied to the vector x, and then you can apply the matrix A to that new vector that you get, and then you can apply, etc. You can keep applying the matrices to the new matrix that you get. This is how it's denoted. So because of the associative property of matrices, we can really just collect all matrices together. So this is the A to the K times x. So in other words, for example, if we're going to rotate, if we're back to the example of something in 2 dimensions, if we're going to rotate something by like 30 degrees, and then you take that new output, you rotate that for another 30 degrees, and you take that new output, you rotate that for another 30 degrees. That's an example of repeated multiplication of matrices and how it applies to transformations. And then the last thing here for the powers of matrices are that if you have a matrix raised to the 0 power, it's essentially the identity matrix. So that's like saying anything to the 0, any real number to the 0 power is equal to 1. That's your additive identity. This is I. Maybe it's 1. It's I.
Is that the, okay, so
which is equal to x.
0. They could be like 10
Yeah.
right?
Yeah.
But a 0 is 1, 0, 0, 1.
Yes.
So weird.
It is.
So it's not like what usually.
Well, it is kind of, because if you take 5 to the 0, that's equal to 1. So the number 1 is like equivalent to our identity matrix. And then this could be equivalent to any matrix that we're talking about.
I was now setting in that the identity matrix is like a 1.
Yes, exactly. And that's what we want. We want a multiplicative identity for the matrices. And that's the 1. It's like the 1 for...
Raise your hand if you already knew about it. Okay. Thanks.
It's okay, Brian.
Just curious.
It's all right. Okay. So yeah, I'm thinking about this example about the rotate. Yeah.
Sorry.
No, it's okay.
Why is K only an integer?
Oh yeah, we don't have a way to like 1/2. 3 to the 1/2 power is equal to, that's a square root, right? Yeah, just want to make sure. I thought it was denominator. This is a square root of 3. We don't have a way to take a square root of a matrix.
And now that I think of it, that looks non-linear.
Well, I don't think it's about the nonlinearity of it. I think it's just about the definition of it. There's for
We're just on matrices.
yeah, for matrices so far we define addition, scalar multiplication, and multiplication of the matrices with itself as long as they're the same size or as long as it's appropriate size. And so doing radicals and for that matter logs and other things are not defined here, and we're not going to do that in this class. And I'm trying to think if it's ever defined in some other way that would make sense, and I can't think of it. Maybe it is defined in some other way, but I've never seen it. So the integer powers are the only power. Now we can go negative integers, so we'll define the negative exponent when we start doing inverses, but we don't have a definition for rational numbers. Okay. All right.
How soon can we do the negative powers?
Like in 10 minutes. Yeah. Maybe longer now that I'm thinking of an example. So let's quickly do an example where we do a rotation of 90 degrees. So remember the rotation matrix? Your A is going to be equal to cosine of 90 degrees. Is that pi? Pi over 2. Is this negative or the other one? Negative pi over 2, negative sine pi over 2, sine pi over 2, and cosine pi over 2. So if we do this twice, whenever I say just rotation, this is automatically counterclockwise. And then if I do clockwise, then you have to throw a negative sign somewhere. If we do 3 rotations, that would be equivalent to A raised to the 3rd power, right? So we do it one time, we do it twice, that would be a 90, and then another 90-degree rotation, that's 180, and then we do it one more time, and that's your 3rd rotation. So if we were to multiply this 3 times, is this easy? What's cosine pi over 2? 0. Sine pi over 2 is 1, right? So this is negative 1, positive 1, and 0. So what we want to do is we want to imagine multiplying this out 3 times. And so that's what we'll do. Let's do this 0, negative 1, 0, 1. Oops, 1, 0. 0, negative 1, 1, 0. 0, negative 1, 1, 0. I'm glad I did pi over 2 instead of pi over 4 because I have all the square roots and stuff. Of course, you can factor them out too, but we should have done that so we can practice factoring things out. Anyways, let's do this 2 at a time. Remember how to multiply matrices. We're going to do the row for the first matrix and the column for the other, and then we'll do it the first 2 matrix first. So 0 times 0, negative 1 times 1, so that is negative 1, and then 0, 1 dotted with 1, negative 1, 0, so that's 0. And then the bottom row, 1, 0, 0, 1, I think that's 0, 1, 0, negative 1, so that's negative 1. Okay? So that's these 2 matrices. Now let's get that third one into it, and then now let's multiply these 2 new matrices. This is a squared times a, that makes a cubed. And so the first row, the second, the first row, the first column, and that's 0. The first row, negative 1 times negative 1 is positive 1. The second row, the first column, that's negative 1 again, or negative 1, and then 0, 0. Okay? So this is our a cubed. Let's check that 3 rotations, or 3, let's rewrite that as rotation 90 degrees 3 times is equivalent to 90 plus 90, 270, yeah, thanks. Is equivalent to a 270 degree rotation, right? And 270 is, what is that, 3 pi over 2? So we could say that this transformation, let's call this transformation B, this transformation where we do a rotation of 270 degrees is really equal to the cosine of 3 pi over 2, negative sine 3 pi over 2, positive sine 3 pi over 2, and cosine 3 pi over 2. So 3 pi over 2, you can look at it a bunch of different ways. That's the negative y-axis. So the cosine is the x value. X value is equal to 0. The sine is the y value. The y value is negative 1. But we want a negative 1. Negative 1 and 0. So it matches. I mean, this isn't a proof, but this is just an example of figuring out what happens in the transformation when we do the rotations, for example. Con?
So is it like on the test, last test, you supposed to do like this?
Not necessarily. I think in the test I just wanted you to find out where the new points were going to be by drawing it out. So I think in the test situation I wanted you to say this vector here is going to get extended by 3, and then it's going to rotate pi over 4 degrees this way. So this is going to be your new point. So I think I wanted you to find this new point, and then that would be the new vector that you're going to run into. So I think this is 3 over root 2 and negative 3 over root 2, or something like that. So that's what I wanted you to do, and these will end up being columns of your transformation matrix. All right, so that's the deal with powers. So the next topic or the next idea is that matrices is really just a collection of numbers that we have, and the numbers are placed in a two-dimensional array. And so there's this other thing that you could do with a matrix called transpose. And the transpose of the matrix is simply switching the rows and the columns. So making your rows into columns, making your columns into rows. So when you do a transpose of the matrix, there's a bunch of numbers that aren't going to move. You know where they are? In the diagonal, they're not going to move because the diagonal has the same the row and the column in the diagonal are the same, so they're not going to move. So you're essentially switching the x or the rows and the columns. So you're switching the rows and the columns, and the diagonals don't move. I guess this is we can actually come up with a real example. 1, 2, 3, 4, 5, 6. If you want the transpose of that, then you're literally switching the rows and columns. So since there's 2 rows and 3 columns, now you're going to switch the matrix, and the matrix now is going to have 3 rows and 2 columns. So 1, 2, 3, 4, 5, 6. Okay? So that's the transpose. And the transpose of a transpose will get you back to the original matrix. That kind of makes sense, right? You take the transpose of 1, 4, 2, 5, 3, 6, and then you're going to switch rows and columns and go back to 1, 2, 3, 4, 5, 6. The sum of the transpose of a sum is equal to the sum of the transpose. So that seems obvious, but it probably should take a little bit of work to try and prove. For any scalar, the transpose of a scalar matrix multiplication is the scalar taken out and then the transpose of the matrix. So the first two seem like they're obvious, but you know, we could check it out and make sure that it actually works. The last one, on the other hand, I think is the trickier one, the trickiest one, and that's to say that if you have a matrix multiplication, the transpose of a matrix multiplication is the multiplication of the matrices, but in backwards order, in reverse order. Remember that matrix multiplication is not commutative, so whenever you see a switch of terms or with switch of factors that you're multiplying, you have to take note of that, because saying BT times AT is different from saying AT times BT. Now, that would work if they commute, but in general, matrix multiplication is not commutative, so we have to make sure that that is going to work out. So we should, I guess, maybe try to do an example. And for that, let's just do a multiplication of let's take this matrix 1, 2, 3, 4, 5, 6, and let's take B. So B has to have 2 of something, Which one is it going to be? The 2 rows or 2 columns? Or 3 rows or 3 columns? I forgot.
It needs to have 3 rows.
It needs to have 3 rows. So let's do 3 rows. And I'm going to switch it up. I'll make it a 3 by 3. 1, 4, 7, 2, 0, 5, and 0, 2, 3. Maybe I should have put more zeros there. All right. I think this is going to be a lot of work, so I need more room here. No, I like the zeros. I'll stick with the zeros here. All right, so let's do AB first and do that computation. So this is a 2 by 3 and a 3 by 3. What's it going to end up being? It's going to end up being a 2 by 3, right? It'll have 2 rows and 3 columns. All right, so the first one, 1, 2, 3, dotted with 1, 2, 0. So that's 1 plus 4 is 5. 1, 2, 3. So that's 4 and 6. That's 10. And this is a 7. This is a 10. 7, 10, 9. 26 things. All right? So that's the first row. The second row, 4, 10, 14, 16, 12, 28, 24, 25, that's 49, 28, 28, 25, 53 plus 18, 71. Wow, you did all that. All right, I hope that's right. So that's AB, and so AB transpose is going to equal to 5, 10, 26, 14, 28, and 71. So now let's figure out B transpose. That's 1, 4, 7, 2, 0, 5, 0, 2, 3. I'm reading it downward. This is transpose. A transpose is 1, 2, 3, 4, 5, 6. So B transpose is 3 by 3. A transpose is a 3 by 2. What's the result going to be? 3 by 2, which is what our AB transpose is equal to. So that's a good sign. And now let's actually multiply. So B transpose, A transpose will equal to, take my row and my column. So the first row, first column, 1 plus 4 is 5. 1, 2, 0, and 4, 5, 6. That's 4, and 10, that's 14. And then now I have 4, 0, and 6. 4 and 6 is 10. 16, 0, 16, and 12, that's 28. And then now I have 7, 5, 3, dotted with 1, 2, 3. That's 7 plus 10 plus 9, 26, and then last one's 71. So it's the same, it's equal. Again, this is not a proof. I mean, we can prove it using numbers and stuff, but even then, this should work for any size matrices as long as they're multiplication compatible. But that is an interesting property because it was switched. I mean, if you even try to multiply A transpose times B, I don't think that'll work because I only have 2 columns for A and 3 rows for AT. I only have 2 columns from AT and 3 rows for BT, and so already that's not gonna, the A transpose B transpose multiplication doesn't work. Does not exist. Let's do a D and E. Okay. So, interesting. Any questions? All right, let's jump to inverses now. And just because we're dwelling on this this property over here, how this order of the transposes switch in multiplication, the same thing is going to happen for inverses. We'll see how that works out. All right. So let's jump to section 2.2 when we're talking about inverse. So the beginning definitions are just terminology that we should be able to use and be comfortable with. If you have a matrix A that's an n by n, it's called invertible if you can find another matrix C so that if you multiply A times C or C times A in any order, you're going to get the identity matrix. In this case, C is called the inverse. Now, we're not going to call it C anymore because the notation that we have for inverse is A with a -1 power. And it turns out that that is a convenient notation for us because it's like multiplicative. I don't want to call it reciprocal, but you can kind of think of it as a reciprocal. It's hard to talk about reciprocals, though, because we don't have fractions in matrices. We don't have a matrix. We can't think about a division of matrices. It's all defined by multiplication. So when you see a negative power, it starts going into what's called the inverse. Okay? So it turns out that if your matrix is invertible, then it has an inverse. We'll call it A sub 1, or A to the -1 power. And it turns out that if it has an inverse, then that inverse is unique. And that means if you try to look for the inverse, you're going to find one matrix for its inverse, and it's not going to be anything else aside from that. So that's the basic idea behind inverses. And the process of finding inverses, turns out that they'll talk about the process after they show you the inverse for a 2x2 matrix. So the inverse for a 2x2 matrix turns out to be a nice formula where it follows a pattern. So if your matrix is A, B, C, D, and assuming that this AD minus BC doesn't equal to 0, then your inverse is going to be a constant 1 over AD minus BC times. Now something happens to this matrix A, B, C, D. It turns out that you switch the diagonals and then you put a negative in front of the wings. Switch. So I always remember that by saying switch diagonals, negative the wings. It's like something that I eventually memorized over time. So for a 2 by 2 matrix, it turns out to be a simple case. You switch the diagonals, negative the wings. And by the way, AD minus BC, that number, is the determinant, which we've seen before, haven't we? So AB, or AD minus BC. So keeping with our rotation theme, our 90-degree rotation matrix, you remember what that was? A was equal to, what was it? I forgot now. 0, negative 1, 1, 0. So that was our 90-degree rotation. Now, if you imagine a 90-degree rotation and you want to do something to that 90-degree rotation to get back to the original position, what would you do to go back? If
You go back 90 or go 270 forward.
so you can go 270 forward or back 90, negative 90 degrees. So what I was saying is that if you have, if we do a rotation by 90 degrees, how would you want to go back to the original position? You'd either rotate it 270 or rotate it back 90 degrees, right? So that's what we want out of this rotation, is that if we're going to rotate it 90 degrees, the inverse would be a negative 90-degree rotation to get back to your original position. So let's use this rule to see if that's what we get.
Fraction out in front, it's part of the formula.
It's part of the formula. So the denominator here would be 0 times 0 minus negative 1 times 1. And then we switch the diagonals, so they're both equal to 0. And then we're going to negative the wings. So negative 1, negative, negative 1 is positive 1. So this will turn out to be just 1 on the outside, right? 0, 1, negative 1, 0. Well, let's check that. A negative 90-degree rotation, A inverse, should be equal to cosine of negative pi over 2, negative sine of negative pi over 2, positive sine of negative pi over 2, and cosine of negative pi over 2. I'm using negative pi over 2 to represent the negative 90-degree rotation. And cosine of that is 0. Sine of negative pi over 2, since it goes down, it becomes a negative 1. And then there's another negative 1 over here. And another negative sign in the formula. And this is negative 1. So again, we verified using some sort of transformation that they're the same thing. So the real way to check this is to actually multiply these two, this one and this one, because A multiplied with A inverse, in this case, should equal to the identity element. Okay, we're not going to do that. You guys can do that. That's actually a good test question. To prove this, if A was equal to A, B, C, D, and then A inverse is equal to this, then if you multiply that, you should get the identity. All right, so that's the first case of inverses. If we have a 2 by 2 matrix, then that's great, that's easy, and that's done. If you have a 3 by 3 matrix or a 4 by 4 matrix, then it's a little bit more challenging, but then we have to establish some sort of process because we do want to find inverses of things. And so we're going to check out the process for finding the inverse of larger matrices.
What do you do for a proof? Just an example, or
No, you have to use A, B, C, D
So what you just did, but with the letters.
with the letters, right?
Okay.
So before we go through the process of the algorithm for finding the inverses, let's find out some more information about inverses. Notice I didn't finish the proof here. If A is an invertible n by n matrix, then for each B in Rn in the output, the equation AX equals B has a unique solution. It's equal to this. So it has a solution. Not only does it has a solution, but it also has a unique solution. That means when you're doing this, you shouldn't have any free variables or anything like that. So the solution exists because here's a proof of if AB is substituted in for X, or if A inverse B is substituted for X in your original equation, then you have A times X, and then that's associative, so you can combine A times A inverse. And when you work that out, because they're inverses of each other, that should be the identity. Identity times B is equal to B. So to prove that the solution's unique, let's not worry about that. The way I would prove it is I would assume that you have a different solution, and then to show later on in the end that the solution is actually the same. That's the uniqueness is saying. To prove that this statement over here, prove the solution is unique, show that U is any other solution, then U must be equal to this. Yeah, but they didn't show it. I didn't show it. But the rest of the proof is in the notation, or in the PowerPoint presentation. All right. Yeah.
Does invertible mean it just has the same amount of rows,
Say it again.
What is invertible?
Invertible means you can find the inverse. That you can get the inverse.
We don't really deal with anything besides 2 by 2. Yeah.
Not yet.
Okay.
So later on we'll find out how to find the inverse of a 3 by 3 matrix. So let's do an example for this one. Example of something that we already know of. So we have A is equal to 0. Was it 1 or negative 1? Negative 1, 1, 0. And A inverse is equal to, dang, negative the wings. So it should equal to 0, 1, negative 1, 0. So let's find out what happens. Let's say in your image, in your output, you have this vector pointing to 2, 3.
The question, your definition of A inverse doesn't need the fraction to come from?
Oh yeah, but the fraction we figured, this is from last page, and the fraction that we got was 1 over 1.
We're solving for it.
Yeah. So in this particular scenario, we'll let B, the vector B, equal to this thing. And now the question is, what vector X, I don't know exactly, this is a 90-degree rotation, right? So what vector X do we have so that it rotates 90 degrees to this? So that's the question that they're asking. So the question is AX equal to B, the matrix, the rotation matrix applied to X. Oh, can I use, should I use X1, X2? Can you use XY? We're used to seeing X1, X2, but in this case we'll use XY. So this is the question that they're asking. The question that they're asking is what XY value do we multiply by the matrix as the matrix applied to get our output of 2, 3. According to what's given here, to find our X vector, we simply multiply the B vector by the inverse matrix on the left side. So if we get our inverse matrix and multiply it by 2, 3, we should get our XY value, we should get a 2 by 1 vector or 2 by 1 matrix that will give us a solution. And that would be 3, negative 2. And that kind of makes sense if this is 3, negative 2. That being rotated becomes 2, positive 3 in the first quadrant. Rotated 90 degrees. Okay? So that works out. Any questions? Are we good so far? We're kind of running on the same theme of an example because it's a 2 by 2 matrix and it's a rotation matrix, so we can visualize it, and so it seems like it's a natural thing to do. All right, let's move on. We got some interesting theorems or properties that we get from invertible matrices. And I've alluded to the second property here as something that matches in one of the transposes, and then even the last one is a combination of transposes. So let's take a look at these properties. The first one is pretty kind of straightforward, right? It's the inverse of an invertible matrix. The inverse of an inverse is the original matrix. The second one matches that transpose property. The inverse of AB is equal to B inverse times A inverse. So it's the product in reverse order. The product of the inverses in reverse order. Now, you can generalize that idea. If you have more than two things that you're multiplying, say if you have 5 things that you're multiplying, you want the inverse of the product of those, then that's equivalent to the product of the inverses of those multiplied in reverse order. It seems like a silly thing to think about, like when will we ever have to multiply 5 matrices together? Well, it turns out that if not by the end of today, by next time we'll be multiplying 5 matrices and finding the inverse of the product. And then the last property here talks about the inverse of a transform or a transpose. The inverse of a transpose is the transpose of the inverse. So it really does look like the inverse and the transpose are intimately connected. Okay, so those are properties of inverses. We will be using some of these properties. The idea behind these theorems is to use these theorems to prove other theorems that are related to, well, more inverses or other things. All right, what's next? Oh, proof exercises. Do it yourself. Actually, I think we might be able to prove B, the simple version of B. Let's see. Let's make an attempt at that. So let's assume that we have AB applied to vector x, and we're going to get another vector b out of it. According to one of the theorems that we had earlier, this is equivalent to saying x is actually equal to the inverse of whatever that matrix is times b. Is that correct? Oh, that's right. Why not? All right, now let's try to approach it in a different way, in that saying that the matrix multiplication is associative. And I'm going to regroup this to say this is bx, and then a is being applied to a new vector bx. Right? So now we can do the inverse business again, that bx is equal to A inverse of B, right? And now, if we take a look at A inverse of B as its own, as a vector in its own right, and then apply that inverse again to say B, to get x by itself, we would move the B over with the inverse on the other side. And now we can just redistribute or reassociate what we have applied to B. So now we see that our x is equal to this matrix AB inverse, which also happens to be x equals B inverse times A inverse.
So
That matches.
we can't move B over first.
No, because it's in between A and B. You can't switch the order of A and B. So you can't, in looking at B, you can't just move B over to the other side because the order matters.
Yeah.
And the way to get things to the other side is to apply something on the left side.
We can't. Can we move X?
Well, x is what we're solving for in this case. So we're trying to get x by itself, so we're peeling away from the left-hand side to get x by itself.
Right. That's our objective. I'm just wondering the mechanics of it. Is it allowable movement?
No.
Left to right.
Yeah, it's not allowed because it's x is being these matrices are applying to x, are being applied to x. So you
have to apply the inverse to get the A off of X.
And then-
You open both sides by inverse A.
right.
Do it. Okay.
Okay. All right. So let's see if we can check out what's next. We're moving closer to being able to develop an algorithm to find the inverse of a matrix. And it turns out that one of the ways to do this is to do elementary row operations. Remember the elementary row operations from the beginning? It turns out that there are 3 elementary row operations. I don't know if we knew that already, but there are 3 elementary row operations. One row operation is to multiply a row by a constant. So remember that move that we do to get the reduced row echelon form, where you have the pivot, it's not a 1 yet, so we would multiply by 1/2 or something to make it into a 1. So that's multiplying a row by a constant. Just a row, not the whole matrix. Actually, let me do a quick simple row reduction process here. Let's see, 2, 0, 0. 0, 1, 3. No, I want this to be that. and
0.
0, 1, 6. No. Okay. So let's do some elementary row operations. What would you do here? Switch the rows, right? Switch R2 and R3. So 2, 0, 0, 0, 1, 6, 0, 0, 3. What would you do next? Multiply the first row by 1/2. You could also multiply the third row by 1/3, right? So it's not quite in reduced row echelon yet. What's the last step? -6 plus R3, -6 times R3, and then add it to row 2, right? All right, so these three basic row operations are exactly the row operations that they're describing over here. So the switching two rows is a basic row operation. Multiplying something by a constant is a basic row operation. And then multiply one row by a constant, add it to another row is another basic row operations. So these are three these are three elementary row operations, and what we could do is we can actually represent these row operations by a matrix. And the matrix that we would represent it by would be what would happen if we do that row operation to the identity matrix. So let's take the identity matrix. Let's do this multiply by a constant business. Let's take the identity matrix and let's multiply the first row by 1/2. So I'm going to call this the identity matrix. Yeah, we're still going to care about the order. Well, I'm just going to do it as 1, 2, 3, and then I'll pick which matrix to multiply by. All right. Identity matrix, and we want to multiply the first row by 1/2. What is the new matrix going to be? So the identity matrix in 3 by 3? 1/2.
0, 0, 1, 0, 0, 1.
Okay. Switching rows and rows. So what if we started with the identity matrix? We want to switch row 2 with row 3. What's your matrix going to look like now? We'll just switch the third row
Start over.
and the second row. Right? Yeah. Yeah. It's going to be a sequence of linear transformations, and we're going to apply it to the matrix that we have. Exactly. And then the last one, multiply one row by a constant and add it to the other. So let's take our identity matrix, and let's multiply the third row by -6, and let's add it to the second row. What's that matrix going to look like? 1, 0, 0,
And
0, 1,
6.
negative 6, and then this one stays the same. Okay? So these are examples of elementary matrices. These are elementary matrices because there's one row operation that you would do to the original identity matrix to get this. Okay? Yeah?
So we're going to do it in that exact same way?
Well, we're going to do it in the order that we did here. So let's reorder, let's call this step 1, step 2, step 3, and step 4.
So why draw the matrices?
Because that's what somebody told me.
No, that's not.
Because if I had the identity matrix, that's what I'm starting with here, right? I'm always starting with the identity.
Does like why does it look like the original matrix maybe like that? Or whatever step.
Oh, we're kind of ignoring this right now.
Oh, okay.
But I'm stealing the ideas from what we did as examples.
So it's the same process, but not the same.
Yeah. Actually, so what we're talking about, so what I'm trying to do is I'm trying to always start from the identity matrix. And now what I've found are these 3 examples. These are examples of what's called elementary matrices. These are elementary matrices because they came from the identity and I only did one row operation on them. So what I'm planning to do is I'm planning to apply that, multiply these matrices to this to get the identity. Okay? So these are just examples of elementary matrices.
So on the calculator, I could make one date augmented matrix, identity, and my thing, and then do row reduction. And then just got to keep track where the plots are, and I can read it off.
I think so. I think I might have lost you somewhere along the way. All right, well, let me go to the next page. Maybe if I restate what I'm trying to do here.
So you have the augmented matrix, like the identity,
Uh-huh.
and your A matrix.
Oh, you're thinking ahead to the actual process.
And then on a calculator, we can row reduction. On this augmented matrix, you can read it off.
Right. And then you'll get the identity on the other side. So what he said is something that we're going to talk about in a few minutes. I'm not quite there yet. Okay, so elementary matrices. Let's call this E1. And that example that we had of the elementary matrix where we multiplied one row by a constant. Wait. Let me change the subscript because I kind of want to go in order here. I'm trying to set this up. So I don't know what the subscripts are yet. The other one was when we switched rows. That's another example of an elementary matrix. The other one was when we took a row and then we multiplied it by something and then we added it to another row. And let me add another elementary matrix. And I think one of the other elementary row operations that we did was we multiplied the last row by 1/3. Right? All right. So these are examples of elementary matrices. So now let's take our matrix A, and I'll use the same A matrix that we had before. 2, 0, 0, 0, 0, 3, and what was the last one? 0, 1, 6. So I'm going to call this, I'm going to put numbers on these now. I'm going to call this E1, the one where we switch rows, because that's the first move we did, right? So if you take your matrix A and you multiply that by E1, what you're going to get, amazingly enough, if you do this multiplication, is going to be your matrix A with the elementary row operation applied. So let's do this multiplication. 1, 0, 0, 2, 0, 0, so that's a 2. 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 3, 6, right? Now my second row and the columns, 0, 0, 1, 2, 0, 0. None of them happened. 0, 0, 1, 0, 0, 1. That didn't happen either. 0, 0, 1, 0, 3, 6.
You get a 1 in the second. Sure.
Oh, yeah. 0, 0, 1, 0, 0, 1. Oh, yeah, the ones. 0, 0, 1, 0, 0, 6. And then 0, 1, 0, 2, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 3, 6. So the 3 pops up here. And did you see what happened? So I found this matrix by multiplying, but look at that matrix compared to the matrix A, right? We switched the rows.
And the order matters right here too.
The order of how you multiply matrix matters.
The elementary one.
So I have my A, and I multiply this by E1. Now let's take what the resulting matrix here, and let's multiply this resulting matrix Let's multiply this resulting matrix by another matrix. Let's multiply it by, what do we do next? Oh, let's multiply it by E2, and let's call this matrix over here E2. Now E2 is a 1/2 0, 0, 0, 1, 0, 0, 0, 1, and we'll multiply that by the matrix that we just got. And when we do that, we'll see that the first row becomes 1, 0, 0, and nothing else will change. Right? So now let's take that new matrix that we just got, 1, 0, 0, 0, 1, 6, 0, 0, 3. Let's multiply this by another elementary matrix, E3, and let's call this last one E3. And you know what you're going to get, right? You're going to get 1, 0, 0, 0, 1, 6, 0, 0, 1. I'm just expediting things a little bit. And so now you take that new matrix, and then let's multiply it by E4, or E4 is that third elementary matrix that we have. And then what do you get? Then you get the identity matrix. So let's summarize what we have here. We have E4, E3, E2, E1, A is equal to the identity matrix. Now, if I regroup this, this must be the inverse. Shouldn't this be the inverse? So that's one way to find the inverse matrix, is to figure out, keep track and figure out your elementary row operations to get the identity. Okay? Now what Caesar said earlier is that there's a quicker way to do this instead of identifying each of these elementary row operations and elementary matrices and multiplying it. If you just augment the two matrices together and then reduce, then you're going to get your inverse. And we're out of time, so we'll have to do that next time. Homework is going to be 2.1. This is 2.2, so this won't be due this Sunday, but 2.1 is due on Sunday. Oh, yeah. Edgar already asked, and I forgot to do it. So I'm going to open it up right now.
So just the elementary is multiplied, not